finish up that proof and then talk about some homework problems. We didn't get a chance to because of the fire drill. So I want to show that T is a zero transformation. And I know since V1 through VP span Rn, we need to make precise the idea that every vector is made out of them. Well, we write an equation. We turn that into algebra. And then we do what we always do with equations is we do the same thing to both sides. We want to prove that T of x is equal to 0. And so this is how you often prove something on a sort of a somewhat introductory level. You want to show an equation. You start out with one side, you manipulate to get to the other side you want to get to. So the first thing is we just plug in this more explicit description of the same vector. I talked about making things more explicit as a great example. Into T. Use the sum rule oops. Let me just use one rule at a time. That's using just the sum rule. Then using the scalar rule. And I know that those are 0. And so the whole thing dies. And so I've shown that any vector goes to 0. Because the building blocks go to 0, and everything's made out of the building blocks because of the spanning. Very special that these span. Therefore, everything that's made out of those building blocks also dies. And I only used the defining property of linear transformation. I didn't have to say, well, it's really given by a matrix, blah, 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 fudge around with matrix stuff. It's really a very clean use of the definition of the linear transformation. So, let me just do a few problems from the homework. 17. They define this transformation. They put it all on one line. And we would suspect that this is probably a linear transformation. We could go ahead and check the defining properties. But it's going to be easier if we can write it as a matrix. Okay, can I write that as some matrix times this input? Well, the first output is all zeros. The second output is x1 plus x2. Well, let's see. So that means the second output, that's this row, it's going to match up with 1 times x1, 1 times x2, and zeros here. I'm doing it row by row. In a minute I'll show you how to do it column by column. I'll just make a brief remark. Third output doesn't have any pairing with x1, but it does pair with x2 and x3, but not with x4. And the fourth output pairs with x3 and x4. So that was going output by output. I could have also just said, let's break it up by inputs. What part of this depends on x1? That plus what part of it depends on x2? Oops. That part of it. Plus what part of it depends on x3? And what part of it depends on x4? And so that's going to be, that's x1 times the vector 0, 1, 0, 0. So this, if I just set x1 to 1 and all the others to 0, I've got 0, 1, 0, 0. That's the first column, because that's the output if x1 is on and nothing else is on. 0, 1, 1, 0, 0, 1, 1, 0, the coefficients there. That's the second column, and so on. So you can do it column by column as well. Okay, so there's the matrix for 17. It shows that it's linear because it is given by a matrix. 25, we want to show if it's 1 to 1 or onto. Is this T 1 to 1? So that's the quick way to write 1 to 1, just 1 dash 1. And so in other words, we want to know, if I call this matrix A, is the solution to AX equals B unique? And we have a nice shortcut. We know we can actually just ask about the zero vector. And so we're just saying, is there a unique solution to AX equals 0? And so that would be looking at, we could look explicitly at the pivots, or we could just try to look at the simple structure of this matrix and see if there is a vector that would automatically make it die. Okay. Probably the easiest way to do it is just do it with row reduction. So let's go ahead and do that. Let's see, I don't have a lot of room here. I'll have to erase that, I'm sorry. But we're trying to find out if it's unique. And let's go ahead and do a row switch. Put that at the bottom, because we don't like zeros at the top. And just, I'm going to move everything else up. Okay. Well, let's look at that. That already in echelon form. And I can count the pivots. There's the pivots. There's 3 of them. Here's a free column. That means it's a non-unique solution, so not 1 to 1. We're done with that. And by putting it in echelon form, I can count the pivots and say there's not a pivot in every row. There's a whole row of zeros here. If I put that as an augmented matrix with some before that's not 0, it's not going to work. So it's not onto either. So putting it into reduced echelon form, doing exactly the same kinds of things we're used to. We just have a new interpretation of what that does. I know that I did that pretty quickly, but I wanted to just kind of do a real quick run through of the homework. Okay, got a little time. And then 31. T is a linear transformation from Rn to Rm. A is the matrix of T. And T is basically what we just used. A is 1 to 1 if and only if A has pivot, and it's pivot columns. It's really, when we're looking at 1 to 1, we're asking is the solution to AX equals 0 or AX equals B unique? That's about free variables. That's about pivot columns. And we need to have every column be a pivot column to have no free variables. The number of columns here is n. That's the number of inputs. And we just put in n there. Because having no pivot columns means no free variables, means unique solutions, means 1 to 1 for the transformation. Okay, one more. I want to do just one out of the second section that we had, and then we'll be done. So whirlwind tour. I wanted to do the last one, 12. Number 12. I've got a matrix A is 3 minus 6 minus 1, 2. And I want B some 2 by 2 such that AB is the 0 matrix. And this is really important, that the easiest way to do that would be B is the 0 matrix. And with numbers, if I want to have 2 numbers that multiply to be 0, and I know this isn't 0, then I have to have b equals 0. But matrices are more interesting than numbers. This is one of the very big differences. So A times B, the way we do matrix multiplication, or our preferred way, is we let the whole matrix A act on the columns of B. So I'm just going to do this column by column. And they say, specifically, make sure that you use two different non-zero columns. So they're kind of suggesting to do it column by column. So let's just look at the first column of B. Let's call that like U, and the second column B. So the first column of AB is A acting on the first column of B, so it's AU. So I want that to be the 0 vector. Oh, that's a problem we know how to solve. Find a vector that dies when you put it into A. Now, we could go ahead and do the row reduction thing, but this one's a little easier. There's something special about the columns of A. Now when we do this, if we look at the components, that's U1 times the first column plus U2 times the second column. And so we're asking, again, it's a very important question, can we play these vectors off against each other? Can we play the columns of A off against each other so that we get 0? Well, yeah, we certainly can. If you take 2 times this one and add it to this guy, it dies. So this would be 2, and this would be 1, and there's our first column. Now, you can't do just anything for these coefficients. They have to have that ratio. It has to be twice as much of this as this for that playing off to work. And so they didn't say V had to be drastically different from U, and it won't be able to be drastically different from U. But if I did like 4, 2, or -2, -1, or something like that, that's going to work as well. And so this really does reduce to a standard question. And notice the connection with linear independence. If these guys had been linearly independent columns, I wouldn't have been able to do this. It's because these guys are linearly dependent that I could find non-zero numbers such that when I did this pairing, I got 0. And so that suggests if these columns are linearly independent, I couldn't do this. And that's a true fact.